Alright guys, welcome back. In the last video we have talked about the theory part behind certificate pinning, or the approach behind certificate pinning. In this video over here we will now take a look how it really works. So we will do the practical exercises regarding to certificate pinning. We will learn how certificate pinning works, how we can identify it, and even more, how we can patch it. So this is the purpose of this video over here. So therefore let's go. Let's switch to the Ubuntu VM and then let's have a look into this one. Alright guys, here we are now at our Ubuntu VM and we start with a very basic clean setup over here. So we didn't perform our man-in-the-middle attack yet, neither do we have the burp suite running, nor do we have any IP table rules set. We even didn't plug it in, so this interface is not available right now. The reason for this is the following. If you get an application from the developer and this one is performing a certificate pinning, you are facing a lot of problems. But the problem you definitely do not want to face is having a broken application, just by design. And this happens quite a lot. So you get an application from the developer and you run it without any modified network components in here. And it just doesn't work. This could also be the case for my apps. I mean, they might be not that well programmed. I'm not sure about this one. And therefore, my pro advice is, if you get an application, then just test it on a non-man-in-the-middle network. We can perform this pretty easily. All we need to do is plugging in our USB to Ethernet adapter by having our access point running. So if you plug this in, there we go. Let's see. Okay, this interface is not up yet. Maybe now it's up. All right. Now we've got our access point running. And this access point is routing the traffic through our Ubuntu VM into the internet. But there's nothing in between. This is a regular internet connection, and if the application doesn't work over here, then we have a problem. Or not we, the developer has the problem. Alright? So let's make sure that this application works regularly without any modification. And therefore, let's take our real device, this one over here. And then let's open screen copy. And there we go. Okay, and now let's install this application. You can find this application in the attachment of this section over here, and it's named. Let's find out. I'm not sure about this one anymore. Yes, of course, I named it certificate pinning _hash. So this application is regarding to certificate pinning with the hash approach. In the next video, we take a look at the approach regarding to having a raw certificate in there. Okay. Alrighty, so let's install this application. There we go. And here we can see these nice neon colors, which is now, I guess, pretty up to date. So it has a fancy UI, I guess. Let's see, we are opening it. And here we have certificate pinning. Certificate pinning, send a request. Alright, and let's perform this request. And we have an error. Pinning did fail. Do we have an attacker? No, not yet. We didn't perform anything. But the smartphone has no internet connection. So this application is assuming there's an attacker in between us and therefore the connection got aborted. So we can fix this pretty easily. We go into the home screen, then into settings, Wi-Fi, and then we simply connect to our TP-Link access point over here. Alright, we are obtaining an IP address and now we are connected. Nice. And let's get back into this one. And let's see, a send request. There we go, successful. We have now an internet connection, no attacker in between us, and we get this text. This domain is for use in illustrative examples in documents. So that's the text from example.com. And this text is being printed out over here if there is no man-in-the-middle happening. All right. Okay, before we perform our man-in-the-middle setup, let's have a look with Wireshark. Because in our setup, we are forwarding single ports into the burp suite. So we can forward port 80, 443, or whatever port we like. It might be the case that this application over here is using a different port than 80 and 443. For example, 8443, 8080, 7331, or whatever else. So let's have a look with Wireshark, and then we can forward all these ports into our burp suite, and then we do not miss anything. Alrighty? Okay, so let's type this here. Sudo Wireshark. There's an E missing. There we go. And now let's select this interface, bring the app in foreground, and then we hit send request. Okay, so here we have now the stream recorded in Wireshark, but it's regarding to TLS 1.3. And if we go into this one, right click, follow TCP stream, then we can see this one here is being encrypted. This is what we have talked about, how HTTPS works. Alright, we cannot see anything in here beside the domain. And this one over here, that's the domain. And this one is before the encryption happening, because the application needs to connect to the host to transfer all the certificates, public keys, encrypted symmetric key, and all the stuff. Therefore, the domain is visible even in HTTPS. Alright, now we know this application is communicating with example.com, and this is the IP we see over here. Let's verify this real quick. Host example.com, there we go. 93.184.216.34. Alright. And to make sure that this application is only communicating via port 443, we can apply some filters in Wireshark. So that's pretty great. If we go into this one, okay, now we can click onto a package which has the destination set to 9384 and so on. We can hit the right mouse button, apply as filter, select it. Now we've got all the packages with this IP address as a destination host. And now we can add some end-to-end filter. So we are applying this filter, the IP destination, to this one, together with TCP destination port, this one, equals 443. Alright, now we can see nothing has changed. These are now all connections regarding to this IP address and this destination port. We can also filter for not this destination port, and now we get nothing. This means all connections regarding to this host are based on 443, at least what we have sniffed. If I do some analysis, I let this application run for quite a while. Let's say 20 minutes, clicking all around, try to make every request I can, and then I record everything over here and have a look how many connections we have related to which ports. Alright, to make sure that this one is working properly, let's run this once again with this filter being enabled. And now let's go into the smartphone, opening Chrome within a new incognito tab. And now we are performing an HTTP request because HTTP is not related to destination port 443. Okay, so HTTP example.com. This should be now fetched because we are looking for IP destination, this address, but not destination port 443. This should be port 80 and now be visible. Let's hit enter. There we go. Here we have our connection, so the filter is working. And if we sniff the traffic of this mobile application, not the browser, and this one over here for quite a while, then we can be sure that we fetch everything. Okay? So the whole task regarding to this one is identifying all the connection the smartphone is making with this application. Alright. We can close this one and now we are sure that it's only connecting to 443. Now let's establish our man-in-the-middle setup. So what do we need? We need our Burp Suite first running. It's within Tools, Burp Suite. Okay. We create a temporary project. We use the default settings. And then we go into Proxy, Options. We select this interface, Edit. And then we select 1042.0.1. If we click OK, we can see we are still missing the invisible proxy flag. And this is a very important flag. Otherwise, these packages will not be re-forwarded. So we enable also this one here. OK. Now we have our Burp Suite running on this interface. The thing we need to do right now is forwarding all these packages regarding to HTTP and HTTPS, destination port 80 and 443, to this proxy over here. And we can do this with our, well-famous IP table rule. So let's set this up. And therefore, we simply close this one over here. We're opening a new terminal. And then we need root privileges. Okay. Now we want to create a new IP table rule in the table NAT, Network Address Translation, which means swapping out IP addresses in a package. We want to append a new rule, therefore the A, and we want to create a new pre-routing rule, which means if we get a package on this interface, we want to reroute it. Instead of going directly into the internet, we want to reroute it into our burp suite. This one over here. 1042.01.8080, exactly. Alright, now we need to define the package type. So the protocol is regarding to TCP and the destination port is regarding to 443. If this is the case, then we want to reroute it to our destination, and we can do this by appending -j dnat, destination network address translation. Switch out the destination address of this package if it arrives at our interface. And we want to switch the address to destination 1042.0.1.8080. If this was a little bit fast for you, I have prepared a whole video where we go into this syntax very deep. So we will figure out what every parameter does over here. Alrighty, now we are forwarding every HTTPS request, but let's also append HTTP. Within Wireshark, we have seen this application is not using any different ports. So we should see every traffic right now, if we can intercept it. So let's close this here. Okay, let's put the burp suite beside. That's good. And now we have established our man-in-the-middle connection. And let's hit this button, send request. And pinning did fail. Do we have an attacker? Yeah, this time we do have. So within the dashboard, we can also see TLS connection to example.com failed. So if we click on this one, we can see the second notification, a third. So I get a feeling that this is really related to our setup. Okay, so this application is somehow data mining that it's not being connected to the correct server. So there's an attacker in between this. This could be the reason if you haven't installed the certificate. So this application or this smartphone might not be aware of our authority of this burp suite. So therefore, let's make sure that the certificate is known to the smartphone and it's being trusted. We can verify this by going into the settings, then security, then encryption and credentials, and trusted credentials, user. Port swigger is enabled. So this smartphone definitely trusts our burp suite over here. Let's be sure if you're opening this web browser, a new incognito tab, and let's open https example.com. Okay, yes, within the burp suite we can now see it's highlighted orange. This is our request. It's an HTTPS request 443. So this seems to be working right now. All right. So our certificate is known to the smartphone and is being trusted. But this application, this really paranoid application, this one over here, it doesn't trust us for whatever reasons. So if we click send request, nope, it doesn't accept our certificate over here. Therefore, this application needs to have some kind of comparison regarding to the real certificate and this one over here, the fake certificate. And therefore, we have to reverse this application and we have to figure out how this is being implemented. Let's go into this. Okay, so we close this one over here and also this one. And now, let's take this application from the downloads directory and put it into the apps directory. So we create a new one, certificate pinning _hash. All right, so now we could use JDX GUI or dex2char, whatever you like. When I played around with this application, I had problems regarding to all. So it might be the reason that we are running screen copy, the burp suite, and then another Java application. So you might run out of memory regarding to your Java instance. I'm not sure if this is the reason behind this, but let's try this. So let's see if JDX GUI is handling this one. If this here doesn't work, then we will fall back to the Eclipse approach. I also like the Eclipse approach if we have some large projects. I mean, this one here, that's not a large project, but it doesn't hurt to use the Eclipse approach also for smaller projects. Alrighty. Okay, so the first thing I like to do is checking the manifest. Resources, Android manifest. Okay, so let's see. We are having the internet permission. I mean, of course, it makes a web service request, therefore we need this permission. And then we have one activity, and this is also the launcher activity. So our code will happen over here. We do not have any other stuff right now. All right, if we go to the right, we can see this one over here, Android Network Security Config. We will take a look at this later on. So the network security config it's a really nice approach to perform a certificate pinning. So we can define what type of pinning we want to perform, the whole certificate itself, or just regarding to the fingerprints of the public key. And we can also define certain domains. So this configuration file should be enough to perform a certificate pinning. Therefore, it should be enough as a developer to only rely on the network security config. But yeah, the real world is different. The real world is using libraries, which is absolutely fine. And these libraries also have their own certificate pinning approaches. So most of the time you will find this network security config and a certificate pinning approach in the library that is being used. In this case, we can also identify the library on the package names on the left. So this one is the OK HTTP3 library, and this one is very popular. So I guess 40% of my applications I face are regarding to this library. So yeah, if you can patch this one, then you are pretty good to go. And even if you face another library, I mean, the approach is the same. So we have these two approaches, fingerprint and raw certificate. Okay? Okay, so this was a lot of input right now. Let's recap this a little bit. We have a file called network security config, and this one is being used to establish a certificate pinning. But it might be not enough to only patch it over here, because developers also might implement their own certificate pinning in the Java code. Alrighty, let's try to find the certificate pinning within the Java code, and then we will get back to this file over here. Okay? Okay. So you know what? I guess let's simply start over here. Before we dive into the Java code, let's simply have a first look into this one. I guess this approach is a little bit easier than directly diving into the Java code. So where can we find this file? It's within the XML directory and it's named network security config. So XML resources maybe, XML network security config. There we go. Okay. This looks absolutely nice. We've got our include subdomain example.com. So that's the domain that's being pinned. All right. And then we have a pin set. Okay. Digest SHA-256, and then we have 3 hashes. So this one here is base64 encoded. We can see this at the, or identify this at the equal sign at the end, this padding. So let's take this value and simply try decoding it. Base64-D. Doesn't look that promising, so let's pipe it through XXD. Alright, so this seems to be some hash. This is a SHA-256 hash, yes. Okay, so now's the question, what is this hash over here and how it is being generated? Because if we want to patch it, we need to understand where this hash comes from. Otherwise we do not know what to do and how to create our own hash over here. Okay, we can find this out by taking a look at the certificate from example.com. So let's have a look into this. We are using OpenSSL. So OpenSSL, it's an amazing command line tool and we can do a lot of stuff. Also, we can fetch the certificate from example.com. And that's the certificate that's being pinned. So we need to have our information stored in there, right? Absolutely. Let's have a look. Okay, so we are using OpenSSL with the sclient command. That's the client command that is making a connection to our target. And we also want to provide the parameter show certs. And so we want to print out the certificates of our target. And our target, we need to connect to this one, is example.com on port 443. Because these are the certificates that's being pinned. Let's see. Okay, looks good. We can close this one. Okay, not implemented. We do not care about this one. Now let's see what do we have here. All right, it looks a little bit strange, absolutely. If you are not familiar with OpenSSL, it might look even worse. So that was also the case for me. But I guess we do not need to understand everything in here. Okay, so let's have a look into this one together. What do we have here? We are having 3 depths, so we are having 3 certificates. The first one here is from DigiCert. DigiCert, it's a known authority and it's a trusted authority. So this is the root CA that's creating or signing other certificates. Then we are having another certificate, and this one, it's again from DigiCert. So we are having 2 certificates now from DigiCert. All right, so we will have a look into this one later on. But for now, we just keep in mind we're having a root CA and also another certificate from DigiCert. And then we are having a third certificate, this one over here. And finally, this is something we know. This is regarding to example.org. Did we call example.org? Okay, it's regarding to the same. So example.org and example.com. All right. So these are our 3 certificates right now. Why do we have 3? The reason for this is the following, and therefore let's do this on the graphic tablet because then it's easier to explain what's happening over here. Okay, so here we are back on the graphic tablet, and now's the question, what's going on over here? What's up with example.com? Why do we have 3 certificates? 1 should be enough, right? So if this one has been signed by a known authority, why do we need 2 additional ones? And the reason for this is the following. The first one is from DigiCert and it's the root CA. So this one over here. All right, this root CA has also its public and private key, but now they have some really hard regulations regarding to this one. So a root CA, it's a very important certificate. If this one, the private key for this one gets lost, the internet would be absolutely in danger. Therefore, this private key needs to be absolutely super protected. So we need a really strong lock over here. This one, maybe even better. So yeah, like this one over here. Okay, so DigiCert wouldn't be very amused if this root CA gets compromised. This is something we definitely need to avoid. Otherwise, the internet is broken. Therefore, DigiCert is not putting the root CA on an additional risk. And DigiCert is creating something called intermediate certificate. This one over here. This is our second certificate. This certificate is not that hard regulated like a root CA. Having a root CA is a lot of trouble and losing it would be absolutely dangerous. They create another certificate, this one. This is the intermediate certificate and this one is our second certificate. So this is also being created by DigiCert. And this one is now being signed by the private key from this one over here, the root CA. If this one over here, the second certificate, gets signed with the private key from the root certificate, then this is exactly as trustworthy as this one over here. So both are absolutely trustworthy right now. So we are having an intermediate certificate which is as trustworthy as the root CA regarding to our authority over here, regarding to DigiCert. Alright, the nice thing about this one is this one has of course a new private key. And this one over here. This is of course also a private key which is held pretty secure, but it doesn't need to be held that secure anymore. So this one over here has some hard regulations. This one also needs to be kept safe, but it's not that hard anymore. Because if this certificate gets compromised, we can revoke it via the root certificate. Okay, so now by having the second certificate, we have way less pressure right now. So this one can be now used to sign additional certificates. For example, our third one, which is this one. This one is now our third certificate. And this one is finally regarding to our domain, example.com. So now this certificate gets signed by the private key from the intermediate certificate, by this one here. And by having this chain, we can now establish this trust relationship. So it goes from top down. This one absolutely being trusted. This one also trusted because signed with this key. And now this one is also being trusted because it has been signed by a known or legit authority over here. Alright, that's the reason why we are having 3 certificates. This one here is called certificate chain. So like this one over here. Okay, this doesn't look like a chain, but nevertheless. So this is called a certificate chain. Okay, and the whole concept of this chain is, having this root certificate in a safe place and still building a trust relationship by having an intermediate certificate over here. Now the certificate has been signed. Here we have our signature now. All right, and this is now being trusted. Signed by DigiCert. All right, so that's the reason why we're having 3 certificates. Perfect. Now we have understood this over here, even if we do not understand the OpenSSL client output. But we also do not need to do this. All right? Okay, so let's get back to our Ubuntu VM. Okay, so here we are back at the Ubuntu VM, and now we know why we have 3 certificates over here. We've got our root certificate, this one. Then we've got now our intermediate certificate, which is this one. And we've got our certificate, which is regarding to the application itself. And this one over here, example.org. So the root certificate has created or signed an intermediate certificate. And this one is now being signed by this certificate, and therefore it's being trusted. Alrighty, nice. We can also see those certificates in this output over here. We've got this nice tag, begin certificate and end certificate. And this one here, this is in base64 encoded output. So this is in PEM format. PEM simply means having an ASCII representation in base64. The other format we encounter out there is DER, which simply means a binary representation of this certificate. And so the file endings of certificates are just regarding to the representation of them. Alrighty? So here we have our first one, then we've got our second one, and here we have our third one. But the order is different. And this one is the root CA. Here we have our intermediate certificate, and this means this is now the certificate of this application. This one over here. So let's copy this out and have a look how we can, how can we display this one over here. So we start at the end and go up to the begin. We do it vice versa. And then let's see, I'm opening a new terminal and we go into certificate pinning underscore hash. And here we create now a new text file, which is certificate PEM. All right, we simply copy paste this output into this file over here. And that's all. Now we can close this file. Now we close this file and we're simply opening it with the file browser. All right, here we have now our certificate.pem. If we perform a file on this, and let's see, then it also says it's a PEM certificate. And this is on Linux system, not just regarding to a file ending, because these doesn't matter. It's regarding to the file structure itself. So even if you would rename this one, certificate.pem to certificate.bin, for example, and perform a file command once again, then we can see it's still being a PEM certificate. All right, let's undo this. So from bin back to PEM. Okay. The easiest way to view this file is simply double-clicking it. So by performing double-click, we can see this right now. We can see verified by DigiCert and the identity is example.org. Now let's make this a little bit larger because there's a lot of stuff in there. If we click on details, we can also see when it expires. So at this date, this certificate needs to be renewed. Otherwise, it won't be accepted anymore. This is very important for the administration of this infrastructure that the admin keeps track of this one over here. Okay, so here we can see country, state, and so on. Issuer DigiCert, okay. And here we have now a certificate fingerprint. Ooh, this looks absolutely promising. We've got a SHA-1 and an MD5 hash. So this one here is some kind of fingerprint of this whole certificate. We will have a quick look into what an hash is in a moment. But for now, let's look over this file over here. Okay, next we also got this public key info. And this is now the public key of this certificate. We can see it has an RSA algorithms. These are the key parameters. We've got the key size. This one is a fingerprint of this key, and this one is the public key in a byte representation. Okay, next, let's see. We've got some subject alternative names, so this certificate is also being accepted for example.org or com. This is why we do not get certificates error. Alrighty, so let's see what's else inside the certificate over here. So let's see. Yes, the signature. This is the last, most important part over here. The signature has been created with the private key of DigiCert. So now, by having the public key of DigiCert, we can verify if this certificate has been really signed by DigiCert. So this is maybe the most important part over here. This will prove that this certificate has been signed by a known authority. So in a moment we will figure out why it's not possible to spoof or fake the certificate over here, but for now let's do a quick recap. So at the end we've got the signature over here, and this will prove that this certificate has been signed by a known authority with the private key of the authority. Alright, then if we go up, we can see we have two fingerprints. One is the certificate fingerprint, and this one over here, and one is the public key info, and this also has a fingerprint, and this one over here. Okay, so now's the question, if these are the fingerprints that's being checked in our application, then we need to know how these are being built, because otherwise we cannot create them for our own certificate, and then we can also not replace these values. Okay, but before we dive into this, let's first have a look at what a fingerprint is. And you can really think of a fingerprint like we human have this. And so a fingerprint for us as a human is being an identifier for us as a person. And it's the same for this certificate over here. So a fingerprint is some kind of identifier, and this one is being built up on a hash. In this case, we have two hashes over here. We've got a SHA-1 hash and also an MD5 hash. These are just different algorithms, but the hash principle is the same. And therefore, let's first figure out what a hash is, because then we can understand what these values over here mean, and then we can figure out how we can build them by our own. Don't worry, we do this on a very high level and in a very short amount of time. Alrighty? Okay, let's switch back to the graphic tablet and have a look into this. Alright, so here we are now back on our graphic tablet, and now let's have a look into how a hash function works. Because if we understand what a hash function does, then we can understand everything in our certificate pinning approach. We will know why an attacker is not able to spoof or fake a whole certificate. We will also know why these hashes are being pinned. And last but not least, we will learn how we can create our own hashes based on the burp certificate, that we can replace them with the original one. And afterwards, we can man in the middle this application. Sounds absolutely perfect, right? Therefore, let's have a look into this one. There are a lot of approaches out there trying to explain what a hash function does, and most of them are regarding to colors. But in my opinion, Bob Ross is the only one who should play around with colors, and therefore I like to go with a different approach. This one over here. So we do this very visually on a high level. This might be not 100% accurate, but if we get this point of a hash function over here, that's all it matters right now, okay? So therefore, let's have a look. Alright, so let's start over here, and as already mentioned, we do this very visually. You might think, what? In a moment, but let me try to explain this afterwards, okay? So we start by having an apple. This one over here. Alright, this is a very well drawn apple, I guess. Yes, maybe the best I have ever drawn so far. Alrighty. Below this apple, we've got now our hash function. And in this case, this one is being a mixer. And let's see how good this works out. Okay, I guess that's okay. This is now our hash function. And below this hash function, we have our output. And we store this output here in the glass. Okay, so let's do this over here. If we take our apple and we put this into the mixer, then the mixer, later on the hash function, is performing a bunch of stuff. So in this case, the mixer is making juice out of this apple. And we get this as an output over here. Okay, here we have now apple juice. So this one over here, this is apple juice. Alright, and this is the principle about the hash function. I mean, not making juice, but having the following approach. If we have our input and we put it into a hash function, we get back an output. And so far so good. But now's the important point. In a hash function, we cannot go back. So it's absolutely impossible to get back from our output back to this input. In this case, I never ever be able to make an apple out of this juice back again. I'm not sure about you, but for me, this is definitely not possible. And this is exactly the principle about a hash function. It's a one-way operation. We have an input over here, we perform a bunch of operations and we get back an output. But we cannot get back from the output back to this input over here. This is not possible within a hash function. It would be possible if this one has been encrypted, symmetric or asymmetric. But that's not the case over here. So a hash function is not some kind of encryption. It's a hash function, and yeah, these terms, encryption and hash, gets often mixed together, which is completely wrong. All right? Encryption means we can get back to the input by having the key, asymmetric encryption, whatever. But in hash function, we cannot go back. And this principle, it can come super handy. For example, let's say if we have a web application. And this web application over here, this has now two input fields. One is regarding to the username, and one is regarding to the password. Okay, and now the administrator has this task to store the passwords in a secure way, which means even the administrator is not allowed to view them. Therefore, we cannot use some kind of encryption. Otherwise, the administrator can simply decrypt them and get back the clear text passwords. And this is exactly where a hash function is super helpful. So let's say we've got this database over here. So this is now not a class anymore. This is now the database that's being stored or storing those passwords. Alrighty, this is our database. And all we need to do right now is the following. So we're taking this password of the user and we put this into a hash function. This one over here. Then we get back our output. And this is now the hash. And instead of storing the clear text password, we are now storing the hash in this database over here. So this is now the hash of this user over here. This means if we cannot get back to the clear text password, we can also not see what's the real password of this user over here. Okay? All right. But now's the question, how can we make sure that the user has entered the correct password? And the approach, I mean, it's pretty simple. If the user enters now a password, for example, test, then all we need to do is we need to put this password into this hash function, into the same hash function over here, and then we compare those two outputs. In this case, we can see this one is green and this one is some kind of purple. Let's call it purple, which means these are definitely completely different colors. And it's also the same for these hashes. So these hashes are not even close being identical, which means the user has obviously entered a wrong password. And we can now verify this even if we do not know the clear text password of this user, which is super amazing, right? Absolutely. So I guess this example isn't that bad as I thought it was at the beginning. Let's stick to this one with the web application. Therefore, let's make a separation over here. And now let's get back to the second important part about the hash function. The second important part about the hash function is the following. And let's say this output here, this one, this is the password TESD. So now if the user enters the password over here, test, there's only a little difference in this password, only just one single letter. And now the second important part about the hash is that no matter how identical they are, if they are not being completely identical, the output looks absolutely different. So because we could have assumed over here that the first part might be identical. This one over here is TES and also this one over here is TES. So this part could have been identical, but not within a hash function. Even if we change one single bit in an input value, we get back a completely different output. And this is why this hash function is that useful regarding to certificate pinning. For example, let's say we have our certificate. Now we are hashing certain values in the certificate and we store these hashes. We can now make sure if a certificate is being represented by comparing these hashes with the one of the other certificate, if this one is the certificate we are expecting or not. In case of not, then we can abort this connection. And these are exactly these hashes that's being compared. Therefore, let's have now a look into our certificate pinning approach over here and how this all applies regarding to these hashes. But keep this picture in mind, this one over here, regarding to the apple and the juice. Because this can come handy if you want to analyze or understand what our certificate pinning approach does. Alrighty? Okay, so now let's take this hashing approach back to our certificate pinning. And let's figure out what these fingerprints means and also why it's not possible to fake a certificate. Alrighty? Okay, so we have seen our certificate before, this one over here. And this one consists of very important fields. One, for example, is the common name. The common name is simply just the domain name where this certificate has been created for. In our case, it's simply just example.org. Alright, so far so good. Next, we have also seen that this certificate includes a public key. This one over here. And we now also know why this is the case. The public key will be sent to the client. And this public key will be later used to encrypt a secret which has been created by the client. So the client is sending back the encrypted secret, and only the person who is having the private key, in this case the server, is able to decrypt this package and receive this symmetric key. Afterwards, the whole connection will be encrypted with this symmetric key over here. So this is the reason why the certificate also includes a public key. Then we have also seen this fingerprint of this public key, and now things starts to get interesting. So what is this fingerprint? So the fingerprint is simply just our public key which has been put into a hashing function, this one over here. So if we take our public key and we put it into this hashing function, we get back this output hash, for example. And this is now the fingerprint of our public key. We have learned before, if we change only one single bit in this input, the fingerprint or the output over here will be completely different. So by having this value over here, we can simply recognize or compare if this public key is exactly the one we are expecting right now. So this is now the fingerprint of the public key, some kind of identifier for this one. The reason why we are using a hash and not just the whole public key is a hash is way smaller. So what we do is we simply create a hash of this public key, and now we are appending this hash into the certificate. So this is the identifier of this public key over here. Therefore, let's do this. So we take this one over here, and now we append this also into our certificate. All right. Last but not least, we have the signature. And this one is maybe the most important part over this whole certificate. The signature has been created with the private key of DigiCert. So this is the proof that this certificate is now being trusted by a known authority. This also means by having the public key of DigiCert, we can now verify if this signature has been really created with the private key of DigiCert. The public key is pre-delivered on our smartphone. So this is a known authority, and we have a lot of known authorities, public keys in our smartphone over here. All right, so this is what our certificate looks like right now. Okay, so I mean, this is our certificate on a very high level. There's a lot of more stuff included over here, but these are now the most important fields for us right now. Alrighty? Okay, now let's talk about faking or spoofing a certificate. Why is this not possible? Let's say we have an attacker, this one over here, and the attacker is now creating its own certificate, this one. So the attacker wants to create a certificate for example.org. Alright, this is absolutely no problem. We can create a certificate for whatever common name we like. Therefore, let's copy paste this into our certificate. There we go. Now we're having a certificate for example.org. Next, we need some kind of public key, because this public key will be used to encrypt the symmetric key afterwards. Therefore, we cannot simply use this one over here, because if we copy paste this one in our certificate, let's do this, then the client is encrypting the secret with this public key, and we are not having the corresponding private key for this one. Therefore, we are not able to decrypt this package afterwards. So this is bad. Therefore, we need to create our own public key, and we put this public key into this one over here, because then we also have this private key and we can decrypt this package afterwards. Alrighty? Okay, so let's change this over here in our public key right now. Okay, but this also means we need to provide our fingerprint for this public key over here. But that's also no problem, right? So we simply take our hash function over here, and now we put our public key into this hash function. Then we receive an output, this one over here, and this is now the fingerprint of our public key. I mean, of course, it's completely different because our public key is different. So we take this output right now, this one over here, and we append this into our certificate. All right, we are now having a public key and the corresponding fingerprint. Okay, next, let's see, we've got the signature over here. And let's also copy paste this into our certificate and see if this works out. Okay, and now we have created a certificate over here, and this should work right now. Should it? Well, no. The reason for this is the signature. The signature will be built over the whole certificate. over this whole certificate over here. And this is a very strong cryptographic algorithm that's happening over here. We do not dive too deep into this. But this signature will verify that these data are correct. So that's the reason why the authority has signed the certificate over here. So the authority has put its signature under this certificate. And now, if we change some data in the certificate, like on the right, the signature doesn't match the certificate anymore. Therefore, the signature does not apply to the values over here. And this certificate will not be accepted by any client right now. Because by having the public key of this authority, this DigiCert authority right now, we can verify if this signature is correct regarding to the whole certificate. And on the right, it isn't, because we have changed a lot of values. And we need to change these values because otherwise we are not able to use the certificate. So this is the reason why we cannot simply clone, fake or spoof a certificate over here with different values. Therefore, we need to create our own certificate which has not been signed by a known authority. But then we need to make the application to trust us. So how is this pinning approach working right now? Let's have a look into this one. Okay, so on the top right we have now our self-signed certificate as an attacker. Let's have a look how the certificate pinning approach regarding to those fingerprints. Because if we understand how these values getting checked or being generated, then we might be able to replace them. Alrighty, and let's have a look. Let's say we've got our smartphone over here. And this smartphone is trying to connect to this server. The server is now assumed to be example.org. Therefore, the server is representing the certificate. This one over here. Okay, so we can see this is exactly the same certificate that the client expects to have. Now let's see what the client can pin in this certificate over here. So we have seen two fingerprints. One was regarding to the whole certificate. And this one is simply just putting the whole certificate, and this one over here, into a hashing algorithm. And this output could now look like follow. Okay, if we now take this output into our client application, we can then make sure if this certificate is the correct or the one we are expecting right now. Because we have also learned if we just flip one single bit in this whole certificate, and for example this bit over here, then the whole output will be different. So if this certificate will be now verified, so we put this certificate into this hashing algorithms, the output over here, this one, is now completely different. And now the application can simply check this. So the application is expecting this value over here, but it gets this value. And this means the certificate is not the one we are expecting right now. Therefore, we are terminating this connection to this server over here. So this is one possibility to check if this certificate is the corresponding we are expecting right now. The other one is regarding to the public key of this certificate. So if we take this public key into this hashing function, then we generate a fingerprint of this public key. And now we can take this fingerprint of this public key over here into our client application. So this one gets copied into our client application. Now, if you're facing a certificate with this public key over here, we can be also sure that this is the certificate we are expecting right now. Because otherwise, if the attacker leaves this original public key in this application, I mean, this is the one that's being used to encrypt the symmetric key that has been created by the client. We have extensively talked about this in the HTTPS section. Therefore, the attacker needs to replace this value, otherwise he doesn't get any value out of this connection over here. Therefore, if you check this public key, we can be sure, okay, this is the certificate we want to have. To create our own fingerprints right now, all we need to do is we need to take this attacker certificate and we need to place this whole certificate into this hashing algorithms, or we only need to put the public key into this hashing algorithms. These are the two fingerprints that can be checked in this application over here. The last example is checking this whole certificate. So we can also apply this whole certificate into this client application, and then we can verify if this one over here is the one we are matching at the server. So these are the main two approaches. Checking the fingerprints of a whole certificate or only the public key, or putting a whole certificate into a client application. Alrighty? Okay, last but not least, there's this question. Why should we only check the public key and not the whole certificate regarding to the fingerprint? The reason for this is the following. The certificate will expire in the near future. So I guess regarding to official certificates, they last for 1 or 2 years only. And now if we fingerprint the whole certificate, so every single bit in this certificate, we also need to update our application. Otherwise the certificate pinning will fail because we have changed a value in our certificate, the expiration date. Therefore the output of this hash will be completely different. Okay, so we have learned a lot over here. We have seen what a hash function is. Why is it useful? And we have also seen why we cannot simply fake or spoof a certificate. We have also talked about the pinning of a certificate. So why we are having several different approaches to pin a certificate, and also that the developer has the possibility to include this whole certificate into its application. Alright, so this was a lot right now. Before we finish this video, let's have a quick look on how these hash sums being generated. The one of the public key and the fingerprint of this whole certificate. Because then you can also perform this approach for your Burp Suite certificate on your own, but we will also discuss this together in the next video. Alrighty? Okay, therefore let's switch back to the Ubuntu VM and have a look into this, how these hashes being generated. Let's go. Okay, so here we are back at the Ubuntu VM. Now let's have a look into the certificate file and how these hashes being generated. We start with the first one, which is regarding to the whole certificate. This one over here, the certificate fingerprint. So here we have the SHA-1 hash of the certificate, and here we have the MD5 hash of the certificate. These are different algorithms, but the input was the same, the certificate file over here. Let's have a look how we can calculate this on our own. So we go into this directory where this certificate has been stored. It's within apps, and certificate pinning underscore hash, and here we have it, yes. Alright, now we take OpenSSL, or we are using OpenSSL to take this whole certificate and perform our fingerprinting action. So we take the certificate into our hashing algorithms, and then we hopefully get back the same values over here. So we type in OpenSSL, and then we are using the X509 parameter, because that's a parameter to interact with certificates. And let's have a look at the help, because we might not remember all those parameters right now. Okay, we have our in file. This is our certificate. We've got an input format. Let's see, where's this one? Directly above. We need to provide that this one is a PAM certificate. And then let's see, this one over here, the fingerprint. All right, these are all the parameters we need right now. And therefore, let's do this. So let me make this a little bit larger. Okay, OpenSSL X509. Then we have fingerprint. We've got as in file our certificate file, and as in form we have in PAM. There we go. We've got this SHA-1 fingerprint at the top, and the certificate is also being printed out. If we do not want to have this, we simply provide the parameter no out. There we go. Now we only have this hash. Let's see. 0A28, and it ends with CA2A. If we check this, 0A28 CA2A. Okay, now we know how this hash is being calculated. Nice. So this is the hash regarding to the fingerprint. We can also do this for MD5 by just simply switching the algorithms. Maybe let's also do this real quick. Okay, so all we need to do is we simply need to append the algorithms we want to use. In this case, -MD5. And let's do this real quick. Okay, so here we are back at our command, and if we use this once again, but this time we want to apply an algorithmus MD5. Okay, let's see. There we go. Now we have the MD5 fingerprint, a 3CBA 1ED7. 3CBA 1ED7. Okay, so I'm only comparing the beginning and the ending of those hashes, because then I'm pretty sure that this matches. Of course, it can be the case that it's super lucky that an attacker has provided a certificate with the beginning and ending of those values. But not regarding to this example over here. Now let's have a look at the fingerprint of our public key. This one over here. So here we have our public key info. And here we have the fingerprint of our public key. Okay, so one of these two hashes might be the one that's being pinned over here in our network security config. Therefore, let's also check the generation of this public key and then compare these values with them over here. Okay? All right, so let's see. The public key. Okay. The first thing we need to do is we need to extract the public key from this certificate. I mean, what we can do is the following. We could simply take the certificate and copy paste these values into a single file. But that's not an approach for us right now. I mean, we are lazy and we are hackers. There has to be a different way. And the different way is absolutely correct. OpenSSL. So let's see. Now we want to have the public key separated from this certificate file. Therefore, let's have a look. OpenSSL, we want to perform some actions with this certificate. Therefore, we have the x509 parameter, and by performing --help, let's have a look into this one. And there we go. In pub key, output the public key. So this command will output this public key in this certificate. So OpenSSL x509, as in file we have still our certificate.pam, the inform is still pam, and we want to print out the public key. There we have it. This is the public key and the certificate. Now we only want to have this public key. Therefore we provide the parameter no_out, and here we have it. Now we can save this in a separate file, pub key. Alright. Now we have extracted this public key. Super easy, right? Okay, so now's the assumption. We perform the same actions once again on this public key file. Absolutely. But unfortunately, that's not the case. So this public key is a different file as the certificate. We can also verify this over here. If we perform a file on our public key, we can see this is now ASCII text. And if we perform a file on our certificate.pam, we can see this is now a PAM certificate. So in our approach, we have seen before, there is no such an option for inserting a public key as an import file. It's only regarding to DER and PEM. So to calculate the fingerprint of a public key, we have to take a look once again into the certificate. And here we can see we have a key algorithms, RSA. So instead of using OpenSSL x509, we now need to use OpenSSL RSA. Therefore, let's have a look into this one. OpenSSL RSA help. Okay, we've got an inform. We can see DRPM, but that's not the case. There we go. Public key. Expect a public key as an input file. This is exactly what we want to have. So what we need to do is we need to use OpenSSL RSA. Then we have our in file, which is now the public key. And the inform, sorry, I got confused for a second. No inform, we are using public in. So it's also a little bit confusing for me right now. All right, and the out form, this is something we can provide. We want to have the out form as in binary format. All right, okay. Let's see. Yeah, there we go. This is now the public key in a binary format. We can now use OpenSSL once again to apply our hash sum about these binary values. So if we print them out, we can see them over here. 30, 82, and so on. Are these the same? 32, 30, 82, and so on. All right, these are exactly the same values over here. This step has been correct. Nice. Okay, so now we can apply our SHA-1 sum over this binary content over here, of the binary content of this public key. Instead of using XXD, we are now using OpenSSL once again. And now we want to have the digest of this algorithm's SHA-1. So this will provide a SHA-1 sum over this content. Let's see. There we go. This is now our SHA-1 sum. Okay, let's verify this value. There we go, 5E, A5, E4. If you put them side by side, 5E, A5, E4, and it ends with F693. F693. All right, nice. This is how we can calculate those values, the public key fingerprint and also the fingerprint over the whole certificate. You will find this information also, of course, in your cheat sheet. So you do not have to watch back this whole video. You can find them over here. Now let's compare these values with the one we have seen in the network security config. So what we need to do is we simply need to apply our base64 encoding afterwards. But first, let's have a look if these are really SHA-1 hashes. And let's have a look. And there we go. we've got now SHA-256 hashes. Instead of using SHA-1, we need to provide an SHA-256 hash. Okay, that's not a big deal. All we need to do is simply changing SHA-1 to SHA-256. There we have it. Now let's also perform base64 encoding format about this one. Okay, if we simply append now base64 into this one, this won't work, because the base64 will also include the text over here, standard in, the equal sign and stuff like this. Therefore, we need to extract this value and also perform this base64 encoding about this value. And we can do this by simply providing this parameter dash binary. Let's verify this real quick. Okay, here's now this output. Let's check this real quick. We pipe this to XXD. Here we have now our key. We can see this over here. That's the correct one. Okay. And now we can use, instead of XXD, we can use base64 to encode this. This is now our hash that needs to be verified. So the struggle we have by doing this command over here are the following. We need to provide the correct algorithms. Okay, that's not a big deal. But we also need to keep in mind that the base64 encoding of this output over here should be not about this whole stuff like standard in, equal sign and so on. It should be just about this value. And therefore we need to have this parameter in here, which prints out only the binary content, which is listed over here. By performing afterwards some base64, this one over this value, then we get back our real hash. So this one over here is the final command we want to use to calculate our base64 encoded fingerprint. Alrighty? Okay, and now let's take this value and have a look into the network security config. Let's see. MM29 UA equal. Okay, this is exactly this value, but maybe let's be sure that this is really this value. Yeah, let's paste it in here. So that's the copy pasted value. And if we compare them now, let's do the pure man comparison. So just above, it looks perfect. Yes, so this is definitely the hash that's being pinned. All right, fantastic. We now know how this hash is being generated. We can calculate this by ourselves, and we could simply replace this over here to bypass certificate pinning, right? Unfortunately, there's one last thing we need to discuss right now, and then we have it done this topic, okay? So if we take a look back into the network security config, this one over here, these are now the hashes that's being fingerprinted. This one is the hash from example.com. This might be the hash of the intermediate certificate, and this might be the hash of the root certificate. Okay, if we create our own certificate, or if we are having our own certificate, the burp suite, then we could simply delete them over here and just simply replace it over here. Don't worry, we will do this in the next video just on a practical exercise together. Alright, but the problem with this file over here is the following. The Android system has changed quite a lot, and it has changed pretty heavily regarding to the network security config in version 7 and higher. This means we are now having the following problem. If we take a look at the network security config in the Android developer documentation, and let's do this here. Network security config Android. So here we have a quick introduction into this file, and we will also discuss this in the next video more in detail. I just want to show you the following. The network security config has been changed. And let's see if we go into network security config. There we go. The default configuration for apps targeting Android 7 up to 8.1, but also here 9 and higher, are as following. The applications only trust certificates that are being stored in the system storage. So this does exclude our burp suite certificate, which has been stored in the user storage. Of course, by having root privileges, we can take our burp certificate and put it into the system storage. But this course is designed to work most of the time without root. Therefore, what's the solution for not having root privileges? And this one is mentioned here. We have to override the network security config with this one over here, with these tags, to also trust the user storage in our smartphone over here. So it won't be only enough to simply override these values here with the one of the burp suite, the fingerprint of the burp suite certificate. we need to apply or need to introduce the user storage, the user certificate storage, also to this application. And therefore we have to change the network security config to this one over here. And now you might ask yourself the question, why have we done this whole approach, figuring out how these fingerprints are being generated, performing this on ourselves and replacing them in the application, when we can simply just use this network configuration and get rid of the certificate pinning? The reason for this is that developer often uses an additional certificate pinning in their applications. And this is also the case over here. So if we go back into JDX and then have a look into the main activity, and this one, then we can see over here we have those hashes also included in the Java code. So everything you have learned so far is very important. Because yes, within the network security config, we do not have to adjust those hashes. So over here, we can simply take the approach from the Android developer documentation, this one over here, and yeah, place this into our network security config. Then the Burp Suite certificate will be accepted. Perfectly fine. But now, if we have to deal with the certificate pinning that's also introduced in the Java code, like this one over here, this one, we now need to replace these values with our fingerprints. So in this case, we have 3 of them. And what we can do is we can simply replace all of them with the one of the Burp Suite. As already mentioned, we do this in the next video together. Feel free to also start on your own right now. And yeah, if you want to perform this exercise by yourself. But this is the reason why we got through this whole theory part right now. To understand how these hashes are being generated, that we can deal with them if we find them in the Java code. If there's no hash in this Java code over here, then you can simply just override the network security config and we are good to go. Alrighty? Okay, so now we are finally at the end of this video, which is now pretty long. Absolutely sorry for this one. But I like to provide you as much information as possible, because if you book this course, you deserve to learn everything that's required and even something which happens behind the scenes. Therefore, you are now perfectly prepared with the theory part about certificate pinning. In the next 2 videos, we will do practical exercises that you get familiar with this one, and then you are pretty good to go to get rid of all the certificate pinnings out there. Alrighty? Okay, so therefore I'm looking forward to see you in the next video.